further ado, please, guys, take it away.
Yeah, we're very excited to present the work we've done in previous semesters and what we've done recently. So we are Mobility 1 PEI. I'm Josh. I'm here with Atharva, Mason, Nicholas, and Yao. So first of all, we want to just go through an outline of our presentation. Why do we care about walkability? Why create a new walkability model? How our walkability model scores walkability? What we did this semester, how we're preparing for next semester, and then some wrap up. So why care about walkability? Well, there's been a lot of research as of late on the various societal outcomes and their impact on walkability, looking at health, social relationships, a variety of environmental measures as well. So what we found is, moving forward, that walkability is a really important aspect of urban planning sustainability. Walkable cities tend to have greater levels of physical activity, reduce traffic congestion, foster healthier lifestyles, and overall more vibrant communities. Despite all these important factors, walkability is still difficult to quantify using traditional measures, and as such, there are limited resources for the public to be able to understand the walkability of their own cities with complete transparency. So right now, the most common measure for walkability is walk score. You can access it on the internet. All you do is plug in an address or a set of location, and it gives you a score from 0 to 100. It calculates it basically by the distance to various amenities like shops, grocery stores, cafes, but the methodology is proprietary, so you don't really know exactly what score you're getting. And again, it's by address, so it doesn't really understand neighborhood boundaries. This is an example of Georgia Tech. 68 out of 100 is somewhat walkable. Moving forward, though, we see that with some examples, we don't exactly see a comparable walkability measure. We had a slide, we're missing it here, but in essence, sometimes when you plug in an address, it'll seem like it has a high score, 90 out of 100. You go into the Google Street View and it gives you a very different picture. So clearly the status quo models are missing something. So why create a new walkability model? Forward. Oh, here we are. Sorry, I got mixed up. So this is the example, 4091 Virginia Beach Boulevard. So it has a walk score of 80 out of 100, which is considered very walkable. If we look at the measure, we see a variety of shops and institutions located around the address. But if we progress and look at the street view, we see a very different site. This is obviously not very comfortable for a pedestrian. If you were to cross the street, it might be very stressful. It might be very hot, uncomfortable. A lot of different factors make this a not very comfortable pedestrian environment. So sometimes walk score gets it wrong. Problem is, walk score is an outdated standard for portraying urban walkability. The methodology is unclear and has yet to be updated. So the gap is that it uses overly simplistic, archaic measures that doesn't really address the covariates in walkability. It only understands it within a static urban context, and nowadays there are new technologies that we can use to better understand walkability. So in essence, our objective is to create a comprehensive pedestrian environmental index that uses geospatial data to evaluate walkability and provide actionable insight for urban policymakers and planners.
So now we'll speak a little bit about how our PEI actually scores walkability and how we create our scores. So from a really high level, there's essentially three main steps. First, we collect data using OSM and sensor sources. Then we generate 4 sub-indices. So we have population density index, intersection density index, land use diversity index, and commercial density index. And then we normalize all 4 and integrate them into one overall PEI score. So yeah, in terms of data collection, we use 2 main APIs within our Python script. So we use the Overpass API for OSM data, which is, specific points of interest. So that's useful for land use diversity, intersection density, and commercial density. And then for population data, we use a census API, which is census data, and we use that, of course, for population density index. So yeah, let's sort of quickly go through each of the sub-indexes and let you guys know how we actually calculate the values. So population density is pretty easy, just population over the area of a, whatever land use subdivision you're doing. So census tracts, block groups, counties, whatever. And then commercial density is somewhat similar. So we use the Overpass API to get, commercial points of interest. So schools, restaurants, cafes, banks, etc. We count them up within a land use division. So a census tract or a census block group, and then divide by the area of that land use subdivision.
Yeah, next we have the land use diversity index. This is essentially similar to the other ones. We use Overpass API to fetch the different kinds of land use in a given census area. and then we calculate this value of entropy, which basically represents how diverse the land use is in the area. And then next we have intersection density. Again, similar to the other ones, we use Overpass API to calculate essentially how many intersections are in a census area, and then we calculate the density for that area. And then next, after calculating all these sub-indices, we do a process of normalization. This is so we can put all the sub-indices in a standard normalized way to compare them across cities, and so we can sum them up together in the PEI. So this is essentially our final formula for PEI. It's just adding all the sub-indices together and weighing them all the same. And so that's what we've been working on the past 2 semesters, but what have we done this semester? So I'll start off by saying one thing we worked on was creating and adding new sub-indexes. So one we looked into was a transit sub-index, and this is essentially because there's strong research between public transit availability and walkability. So we found this PTLA, or public transit accessibility levels, and we wanted to test this out and find a way to integrate it into PEI. So this one is slightly different from the other ones. Essentially what we do is we use transit stop data from the mobility data space, and then for each transit stop in a given census area, we calculate essentially the average wait time and the walking distance time, so essentially the total wait time for a given transit stop. Then we find all the stops in a census area and then calculate a score for a census area. And so applying this methodology, we started out by creating a PTLA for Atlanta, which you can see here on the right. We were pretty happy with it, and it corresponded pretty well with transit lines in Atlanta. So after computing this for Atlanta, we went ahead and generated data for the entire US, and we're pretty happy with that. There's still a couple things we want to do moving forward with this. We want to find a way to generate data for previous years, not just 2025, and we'd also like to fully integrate it with PEI.
So another thing that we accomplished this semester was working to make our PEI data a little bit more dynamic. Something that we observed within the current infrastructure of the walkability score is simply that it relies on an archaic and static infrastructure when it comes to urban regeneration. One of the tools that we implemented was a quote unquote what if tool, which essentially takes a certain geo ID of a given block group and allows you to change one of the sub-indices, PDI, IDI, LDI, CDI, and it recalculates your PEI score, allowing you to observe trends in the different block groups to see whether or not there are some detriments to a given area or whether or not there are some unseen beneficial trends within them. And then we intend to use this as a means to explore how different implementations of metropolitan or urban areas can kind of feed on each other and begin to optimize themselves. Here you see the pseudocode, and then this is the output. This is the before and after, showing how these scores begin to be updated just for visual purposes.
Yeah, so in the interest of time, I'll summarize this section here. We wanted to perform a comparison with WalkScore to understand how our model differs with it. In order to do so, we mentioned earlier how WalkScore is address-based, but our model is area-based. So in order to compare the two, we came up with a system of finding a representative point for each study area, in this case, a block group, that represents the a representative point of the block group. And we found the WalkScore at that point and compared it to the PEI score of the entire section. So moving forward, we found this trend, R squared of 0.457, 0.456, so some moderate correlation between the two. Moving forward, though, we wanted to look at a different type of relationship between the two, and that is the Spearman's correlation coefficient, measuring the strength of whether or not one measure increases with the other one, not necessarily at the same rate, but in the same order. So looking into that, running the analysis, we found a Spearman's correlation coefficient of 0.6882, considering it to be strong. There's still more information we'd like to dig into this. For example, like why is it this number in particular? How does each individual subindex relate to the Spearman correlation that we found? All these are future areas of research.
So one big thing from the previous semester that we haven't talked about yet is the web app. So that's essentially we built our web app to allow us to create, a way for external people to access our data in a free manner, something that we talked about that Walkscore doesn't particularly allow you to do with it being proprietary. So yeah, we created a web app in the previous semester. It's deployed. The tech stack's on the top right. If you want to learn more about the web app, you can look at our previous semester presentation. But essentially, yeah, I'm going to talk about a bit about some of the updates we have from this semester. So yeah, the main new thing we have is a city comparison tool. So we thought this was extremely important. People want to see how cities change over time. So you can put in a city, any statistics, and 2 years, and you can sort of see how that city's changed over time. And then another huge thing we did this semester was creating a national data set. So essentially what we did was we ran our, the methodologies we talked about earlier in this presentation across the whole US, and we created, a large data set, particularly for Dr. Koo for his research at Emory, but also, for us. And yeah, here's his 6 cities. I think it's quite nice to look at the maps, quite visually appealing, in my opinion. So yeah, another thing on these maps, I know we talked about transit subindex, but I think it's quite nice to sort of compare, a city, and sort of its transit system, and you can kind of see how, the PEI scores is darker green, sort of along where the transit lies. And that sort of like reinforces RPI as a pretty good metric. Typically in transit-oriented areas, people are less likely to have a car. There's more emphasis on, urban planning and walkability, so PEI scores tend to be higher. On the next slide, yeah, this is DC again. You can kind of see the radial lines as the transit moves out. It almost perfectly follows our PEI scores. In terms of how we store our data, there's 2 main methods: GeoJSONs and CSVs. GeoJSON typically, for visual reasons, and CSVs are just easier to access. Another one thing we did this semester is, in previous semesters, we stored data on the GeoID level, so that's census tracts and census block groups. This semester, however, we shifted to also allow you to aggregate data into a county level. So on the bottom, you can see there we have state FIPS and county FIPS, which aggregates data into county level. And yeah, quickly, just for your visual sake, here's Atlanta subindex scores in 2022. So you have intersection density on the top left, population density on the top right, commercial density on the bottom left, and land use diversity on the bottom right. This is from the web app. And then on the next slide, this overall PEI between 2013 and 2022, and the change in PEI on the left. It's pretty good. So you can see the city's moving in a good direction, which is great.
We've done a great job for this semester, but there are still some limitations that we can still do better. For right now, we haven't decided what are the weightings of each sub-indices, and this would be a topic we are going to research in the future. And also, the data the OpenStreetMap provided is not completely correct. So we will still need to manually validate data for our further research. For so far, we already have PDI, CDI, IDI, and LDI sub-indices. So we will still need more environmental sub-indices to build comprehensive urban information models. Therefore, we will introduce more indices like transit indices and greenville indices in the future. So we are deciding to introduce the greenville indices for the next semester. So it's how much greenery is visible for street level perspective. And it's typically using the images from source like Google Street View. And by analyzing the ratio of the green pixels and total pixels in each images to capture the extent of the vegetation from a pedestrian's perspective. And here are some real cases that related to these indices, and we can do a lot with it, like mental health and other stuff. And here is more topics that we can research with the indices, like this spatial temporal evolution and maybe some neighborhood quality analysis and human settlements or mental health related content. And we can also do it with other indices to research like more topics. And also we have already have a good start for collecting the sampling points for these indices. I guess it will be a good start. And thank you